Good morning, everybody. So I'm Fabio Soci. I'm a second-year PhD student here in Modena. And during my last year, my research activity has focused especially on the characterization of gallium nitride high electromobility transistors. And other activity has been performed on thermal energy harvesting system. In particular, we have developed, realized, and analyzed in deep detail a self-resonating DC-DC converter. This converter is capable to self-start up with very low input voltages, and for this reason can be applied in thermal energy harvesting application and where the thermal gradient is very low. All the application like wearable sensor. However, for sake of time during this presentation, I will not focus on this secondary activity, but I will just talk about the characterization of gallium nitride HAMT, which is the main activity carried out this year. So I will start just making a brief introduction about the gallium nitride by HAMT for power electronics application. Then I will show you how it's possible to obtain normally off operation in these devices. After, I will introduce the issues of threshold voltage instability, and at the end of this presentation, I will show some results that we have obtained using the SCGM technique. Because the continuous growing in the demand of power electric power is becoming very important topic to try to reduce the conversion losses. In fact, it has been estimated that just in the US, the conversion losses are almost the 10% of the total amount of electric power generated. And it can be seen in this chart that the amount of conversion losses is almost the same amount of power produced using renewable sources, just in the US. And a possible way to reduce these conversion losses seems to be to exploit the physical properties of new materials like gallium nitride and silicon carbide, which are wide bandgap semiconductors. And here we can see in this graph some possible application of these two materials. We can see that gallium nitride seems the best candidate for application where the voltage are below 1 kilovolt, while for application where the voltages rise over 1 kilovolt, maybe will be more indicated silicon carbide. The main advantage of gallium nitride is that thanks to its physical properties, especially the wide band gap, as we can see here on the top of the table, we can break the silicon limit, especially the limit that regard the trade-off between the breakdown voltages and the on-state resistance. As we can see on the left, using gallium nitride, we can obtain devices which have higher breakdown voltages while keeping low on-state resistance. And this means that we can reduce the conversion losses during the conversion process. Okay? And there is many other advantages in using gallium nitride instead of silicon as active device during power conversion. Here we have another example, another important advantage is that in gallium nitride HAMT we can obtain very high electromobility and saturation velocity. And this allowed to increase the operating frequency in the converter, and this will lead to reduce the size of passive component, capacitor and inductors. The result is that we obtain a smaller converter and also we reduce the costs. The main problem in the application of these devices to power electronics is that the classical gallium nitride HAMT is a normally on device. This because at the interface between gallium nitride and the aluminum gallium nitride barrier, we have, because of the polarization effect, the formation of a two-dimensional electron gas, which behave like the channel of our device and can conduce the current, even with 0 voltage applied. However, in power electronics, we prefer to use normally off devices, which are more safe in case of failure of the circuit. And so we have to find some way to obtain this normally of operation also in this aluminum gallium nitride HAMT. And many solutions has been proposed. We can see here some examples, but we will just focus on the last one, which is known as gate recess, which is the technique used in the device that we have studied. In this technique, we reduce the thickness of the barrier using the gate recess process, and reducing this thickness beneath the gate, we deplete the channel and we obtain normally off operation. Moreover, an insulator layer is inserted beneath the gate to reduce the amount of gate leakage current. For this reason, this structure is also known as metal insulator semiconductor HAMT. Here in this slide, we can see some current voltage characteristic obtained for our devices. And the important thing is that this characteristic has been measured using dynamic technique. This is not DC characteristic, but they have been obtained using double pulse measurement system. And in this system, we can change the bias point of the device during the measurement. And we can see here that if we use a 0-0 baseline, this means 0 bias voltage for the gate and 0 bias voltage for the drain, we obtain the green line, and effectively we have a positive threshold around 0.5 volt. On the other hand, if we change the baseline and we use, for example, positive baseline on the gate, like in the red line, we have 2 volt, we obtain again a positive threshold voltage, but this time we have a strong shift through the threshold voltage value is over 1 volt. And on the other hand, if we choose a negative gate baseline on the gate, the threshold voltage shift go through negative value. And obviously this kind of behavior is unwanted, and if we have perfect device, we should have that all these 3 characteristics are the same. Many other authors have observed this kind of behavior, this threshold voltage instability, in metal insulator HAMT, and they have found out that the cause of this threshold voltage instability is the presence of traps in the insulator layer. In fact, if the insulator layer presents some trap state, this means energy state in the band gap of the insulator, this trap state can be occupied or capture electron easily from the 2-dimensional electron gas. Because the thickness here of the barrier, because the gate recess, is just few nanometers. Therefore, the electron from the 2-dimensional electron gas can easily flow to this state by tunneling and can also be released. However, when an electron is occupied this state, it behaves like a fixed negative charge. And when we make the electrostatic charge balance on the device section, this negative charge reduces the amount of a viable carrier in the 2-dimensional electron gas. Okay? So every negative charge will reduce the amount of a viable charge here. So reducing the viable carrier in the 2-dimensional electron gas will reduce the current and shift the threshold voltage. And we have observed that effectively when we use a positive baseline, like 2 volts on the top on this slide, we have a large amount of charge trap in the insulator layer, and we have very low, this reduces the density of charge in the 2-dimensional electron gas. And this will lead to less current and the positive threshold voltage shift. If we change the baseline, for example, we reduce the bias on the gate to 1 volt, we will have less charge trap in the insulator layer, and this will reduce the threshold voltage shift. So now I will show you a technique that we have used to gain more insight about the trap in the insulator layer. This technique is called a CGM because during this technique we measure the GM or the transconductance of our device at different frequency and different bias for the gate. We do this by applying a small C signal on the gate of the device, and then we measure the response on the drain side, and we can simply evaluate the transconductance of our transistors. This measurement, as we can see here, is performed at different frequency, and in a normal device we should have this characteristic, the GM over the frequency is completely flat. However, this does not happen because we have the presence of trap, and we can see there is a strong dependence, correlation between the measurement frequency and the GM. So starting from this value, we can extract the oxide trap state density using the model proposed by Sun in this paper. This is a mathematical and physical model which assume the tunneling exchange of charge between the trap state and the two-dimensional electron gas. And starting from this model and the GM measurement, we obtain this trap density, which gives us information about the energy level of the traps on this axis. And on the y-axis, we obtain the position x of the trap state from the two-dimensional electron gas. So concluding, we have make a deep characterization of gallium nitride HAMT with metal insulator semiconductor structure, and we have effectively verified that they can operate with normally off behavior. However, they have the main problem is that there is a threshold voltage instability, and the cause of this threshold voltage instability is the presence of traps in the insulator layer. After we have performed many characterization of these surface traps, insulator traps using many techniques, and here we have seen some of the results obtained using the CGM. So that is all. Thank you for your attention.
What about the main novel results of your work? I mean, you have talked about the properties of electronic devices, but in my opinion, you have not given enough emphasis on the novelty. I mean, I will say, if you have to summarize in a few words, okay, the main result, the main scientific result in terms of novelty of my work is?
Yeah, for example, this is an important result because many people have used the metal insulator structure to obtain normally off operation, but many of them have observed the threshold voltage shift, but they don't give an exact explanation of this, the reason of this threshold voltage shift. They just make some hypothesis of that. We have used many techniques to verify that effectively there is something that happened beneath the gate, and we have found that the behavior of these traps can be associated with traps in the insulator layer. And then we have applied techniques which are usually applied in silicon technology, are never been applied in, or yes, I've been already applying other heterojunction technologies, but never in this kind of structure, and we have obtained this result for the characterization of traps. So we have give more insight about these traps. Okay. Yeah.